Hello everyone, this is the video lecture for Calculus 2, section 8.3, Physics Applications. So, I would say that some of these are going to be easier than others. Some are not, of course. We're going to have two halves to this section. There's two halves, and the first one is dealing with force of fluids. So let me give you the formula for force. It is rho G A D, and this is measured often in pounds. I guess it could also be newtons is another version. I can't remember if we're going to see that or not. Okay, so what is going on here? Well, that's rho. It's a Greek letter, stands for R, makes a R sound. But what that is your density. Your density. G, can you guess? It's gravity. And so because we're talking about metric or standard, we're going to have a different number there at different times. So watch out. A is area. And D is depth. Okay, so how does this work? I have some sheet metal. I'm doing a three-dimensional thing here. Some sheet metal underwater, and it's down some kind of depth. Okay, so the depth, sheet metal area, gravity is a constant, and rho is the density of, say, like of water, which in this particular case will also just be a constant. Okay, so there's one. We also have pressure. Which is rho G D. And again, this is going to be done in like pounds per square foot or something kind of like that. That's a common measurement. And so what's going on is that we're removing the A part. It's everything else, just remove the A. Consider it kind of like a point, okay? Just like a point. Like you're diving down deep in water and you're like, oh man, the pressure is like really high down here. That's true, but that pressure is applied to, say, like your eardrum, which would be some surface area accordingly. And that's what that force would be, say, on your ear. Or if you go down in a submarine. And yes, there's pressure as you go down deeper, but the force depends on the amount of area, and in particular like windows and stuff like that, or the walls, or the ground. So how do we put these together? We have force is equal to pressure times area. Okay, so there's your formula, or I guess you could just say P times A. I have a note here that says sometimes density will already include the gravity. And so in particular, when we're talking about like pounds in particular, this stuff here often gets combined, I think it's those two, because pounds unto themselves already have gravity. So this is just, I hope that you already know this, but I'm just going to do a side note over here. If we're talking pounds in my English Standard, the equivalent is newtons over here. But a lot of times what you hear in metric system is kilograms, right? Blah, 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 kilograms, how heavy, I guess you can say. Well, this is mass. This is not a force. This is a mass. It's the gravity is actually removed. And so the English Standard equivalent would actually be slugs. I don't know if you've ever seen that before. In fact, you're not going to use that as far as I know. No slugs in this class. But these here on the top include the gravity. It's already included. These do not include the gravity. So just watch out as we go back and forth, okay? So you know gravity, 9.8 meters per second squared, that kind of thing. But it's also 32 feet per something. I don't know. 32. So we got a few different varieties, and we might or might not use those. Here we go. Whew. So 83001. Yep, that's your first question on the homework, right? I think. So we have this tank of water, and I'm just going to create this tank here for you. I didn't do very good on my 3 dimensions here. I don't like how I did that. There, let's just do that. That's better. There we go. There's my tank. There. Okay, so I got a tank of water, and this is going to be 6 across. Again, I'm just drawing it so terribly. 6 feet, 3 feet deep. Well, I don't want to say deep because we're doing depth is this stuff here. Depth is 4 feet, by the way. Let's just say wide or long. Now notice, because everything's in feet, we're going to definitely be talking about this, English Standard Version here. And that's going to be gravity included when they're talking about pounds and all this kind of stuff. We have rho, which is, again, my density, which is 62.5 pounds per feet cubed. Now notice the cube part. What we're going to want, say like pressure, is feet squared. Okay, so there is a small difference, and we're going to see that. Again, I want to note, again, that you have gravity already included. So pounds means that gravity is already included. Okay, awesome. So, part A, they say find the pressure at the bottom. So you swim down to the bottom. I know it's only feet, but you swim down to the bottom. What's the pressure at the bottom? Again, that's not including anything area-wise. I guess you could say this is going to be pounds over feet squared, right? Well, what we have is pounds over feet cubed. So how do I get the pounds over feet squared? I simply multiply by feet. So what I'm going to be doing is the 62.5 times the 4-foot depth, and you yield 250, again, pounds per feet squared. That's your answer. Very simple to do. Part B, they want the hydrostatic force at the bottom. Blah, 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 force at the bottom. Well, force is going to be in just pounds. And so what we're having to do is take my pounds per feet cubed density, and I want to go to just plain old pounds. How do I do that? I have to multiply by a feet cubed, a volume, right? That's a volume. So if I multiply by the volume, which in this case is pretty simple, we should be able to get the answer. So 62.5 times the 4 depth times the 6 width times the 3 length, depth, width, whatever. And I get 4,500 pounds. Just pounds. Again, gravity's already included. Part C, they want the hydrostatic force of one of the ends. Okay? And what I'm guessing, I'm just looking at my little diagram pictures that I have here. They're talking about a 4 depth and a 3 width. So that is not the scale. Sorry. They're talking about one of these guys here, this end. So, not the scale, but there we go. What's the hydrostatic force, the force of this, I guess you could say, like this metal plate that's submerged in there? So, I'm going to ask a couple strange questions to start with, and then we'll go from there. What's the pressure keyword, at the top? Sorry. What's the pressure at the top? Right here. So you're sitting at the top of the pool. How much pressure is applied to you? And don't be technical with it. The answer is actually just 0. It's just 0. I know that the atmosphere and all that kind of stuff, but we're just going to go with 0 because, again, we're talking about like 0 height and all that kind of stuff. Again, pressure, if you go back, pressure's got to be some depth, and my depth is a 0. Okay, so I got 0 there. Okay, so what is my pressure at the bottom? And you know what's interesting is we just found this. It was the 250, which we already obtained earlier, right? So we just did that problem, that part A. So then I'm going to ask, what's the pressure at halfway? So in particular, this case, we're talking about 2 feet. Well, then I take the 62.5 times the 2 now, and I get 125. Notice that there's a progression here. I'm going from 0 to 125 down to 250. Yeah, for my pressure. As I go deeper and deeper, my pressure gets more and more true, but it seems linear. It's a linear, but at the same time, it's not a constant, it's a variable. So yes, it's easy to see force. That's what we're looking for. Hydrostatic force is rho, g, a, d, that kind of thing. But my pressure part, I guess you can say like this side, is going to be variable. And because the density and gravity are not variable in particular, it'll be my d that's a variable. And we already know that because my depth varies as I go down. Right? I mean, I guess you could say like, oh, well, my depth is 4. But really, you have a depth of 0, a depth of 1, a depth of 2, a depth of 3, a depth of 4. You got all these variables in there. So variable, you know what that means? It means calculus. Yeah, it means calculus, and in particular, integrals. So let me set this up. I got 62.5 times d, and that's going to be my pressure. Remember, that's my pressure there. And I'm going from my depth of 0 to 4. Cool. Well, that doesn't seem too bad. And so if I get this variable understanding here, what I actually have then is 62.5 integral from 0 to 4 of 1 dy. Now, why did I put a 1 here? Well, I have to put something here. What I'm getting at is this guy here times d. That d comes from integral of 1 dd, let's say. So what's the integral of 1? Well, it'll be here in this case a y or a d. And so we actually get back to the same dimension that we had earlier. Do you see? This was pressure, right? It's the same thing. Now, I don't want to put a d. I want to put a y, of course, from 0 to 4. But what we're doing here is just simply finding pressure here, variable pressure and all that stuff. Well, we're needing the force. We're wanting the force. So actually, all of this is bad. Not really. It's all very good. But it's not our final answer. Again, force would include an area of some kind, right? And right now, what I have is just a 1. And it doesn't really do much. And so what I want to do now is expand on this concept, okay? What I'm going to now say is my force is equal to the 62.5. Integral from 0 to 4 of 3y dy. Now let's pause on this. I replaced my 1 with a 3y. I'm hoping that you're seeing that we're doing a concept here. That's really what's going on, is a concept. What I'm missing between my P and my F is an A. This is my area. I want to find out what the area is of, say, this rectangle thing. So this is a 3 and this is a 4. And I want to know what the area is. Oh, it's 12, right? Multiply them, get a 12. Well, no, because again, we got variables going on, and this guy is always changing his depth. So what we do is I say 3 times my depth, in particular, I'm going to say y. And isn't that the area of a rectangle is length times width, basically? So that's how I'm creating it. So don't just put 3 times 4, it's 3 times y, because that's what's actually changing here. Of course, now I'm going to integrate. And so the 3 comes out to the front, y squared over 2, from 0 to 4. Plug in the 4, the 0 goes away, of course. Easy stuff. You get 1,500 pounds of force, not pressure, force, on that end of the plate. Cool. So what I did just now is the long method. I was trying to explain all this stuff. I was like, oh, hey, let's try to find the pressure. And then now let's try to find the find the force by including the area. And that is a very long process. Surely there's just a formula, right? And yes, there is. We'll get to that. 83005. So, I have my water, and then I have a circle, and this could be just a disc, it could be some kind of a window and a submarine and all kind of stuff. They say this is 7 meters in radius, and I'm under the water by 5 meters. Now notice meters. It's a giveaway, right? That you're going to have to find your gravity now, 9.8 meters per second squared. My rho, they give that to you as 1,000 kilograms per meter cubed. And so what actually ends up happening when I'm going to be doing my integral is rho g integral blah, 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 dy. And then it's going to be equal to something in newtons. Okay? Because again, we're all in metric system all of a sudden. What's funny is that WebAssign actually wants you to fill in these both boxes here. And so in a way, they actually give you the -7 to 7 as well. What they're giving you is a system to work within, but also constraints that you're forced into. I know we're finding force. Kind of funny how that works here. I'm forced into it. Haha. I appreciate them trying to help, but I think that I would do better on my own. And so I am a little upset, I guess you can say. I mean, just peeved that they require me to do some formatting before I could just give them the answer. But it is something that we have to do because it's on there, and I don't make the decisions here. But in a way, they kind of give us some guideposts. So they're going from -7 to 7. And how is that working here? I thought we had a 5 depth. Well, I mean, if I were to do this problem, honestly, I'd say maybe 12 and 5, right? What they're doing instead... Well, no, I'm sorry. I messed up. I'm sorry. Because 12 is actually right here. This would be 19, I believe, right? 14, yeah, and 5. So I personally like going from 5 to 19 for my y, but they're going to do their own thing, and that's okay. I just have to kind of adjust. So right here, though, I'm going to just go ahead and remind you that 12 is right in the middle. Okay, that's, again, 5 plus a 7 will make a 12. And so I need to kind of focus around that 12 later. We're gonna talk about the 12 later. Okay. So what I'm ultimately wanting to do here is find my area. And if I can find my area, this integral here is going to give me my depth. And this stuff was my, well, it's the other stuff. My force requirements, whatever. I don't know. What was it again? Density and gravity. Sorry, density, gravity. Constants, fine. The integral gives us an extra dimension. That would be our depth, our y, and then our area is something that we have to plug in. What am I missing? The area. So I'm thinking, oh, the area of a circle is pi r squared. Boom! Done. Put a 7 in. Yeah, no. Not at all. I'm going to actually leave it up and cross through it because that is not the way to do this problem. Instead, what you're wanting to do is look at this as like a function. Because, again, we're going to be integrating some kind of function to get some answers. Again, I'll have a dy at the end, so I'm going to move the y's over to get an x. So x squared is equal to 49 minus y squared. I'm going to square root both sides. And when you square root both sides, remember there's a plus and minus. I don't really talk about it very much, but that's important. What this x is your width. So on a circle, it's giving the width at any moment. From the middle, of course. Because there's a plus and minus, that's the plus side, and this is the minus side, right? So if I want a total width at any height, like, again, like how far across am I? Like that. total width would actually include both, thus a 2 times the square root of 49 minus x squared. I basically took the plus minus concept and said, well, if there's a plus and there's a minus, I'm going to put them together and say twice as much. I guess in a way you're also saying like absolute value, right? Because you're going to have some over here and some over there. So why is the width important to us? Well, remember the area of a rectangle in particular is going to be width times height, I guess you can say. Width, height, find it. Well, this isn't a rectangle. Yeah, that's true. It's not a rectangle, but it has a lot of rectangles in it. And it's really hard to see, but each one of these actually are little bitty rectangles. And this is how calculus is designed, is that we're, this is calculus 1, like chapter 1 stuff. When we're integrating or taking a derivative, we're trying to find, as the limit approaches infinity of all this stuff so that we can find an accurate Riemann sum kind of answer. I'm hoping that some of this rings bells. So what we're getting at in a way is that we have our width, and we're gonna, when we integrate with the y, it actually gives us the full area here, okay? So that's the problem that I'm faced with. I already have my width, cool, but what is my height? Wouldn't I just put a y in the front? Square root of, or I'm sorry, 2. So 2 times the square root, 49 minus, what did I say, x? That's a y right there, sorry. Y squared. Sorry, I messed that up, that's a y. Obviously, that's a y. Close, close. The problem is that we're not centered here. This is actually centered at 0. And this guy here is centered at 12. If you notice, we have a circle here, plain old circle equation, but this depth is actually at 12 depth, where 0's up here. So either you're going to have to take this guy and shift them up so that you're centered at 0, or shift it down or something, or we can change our height around. And so what they propose, and this is a good proposal, is not just y, but instead 12 minus y, okay? So this 12 minus y in particular, what it's doing is shifting it down the 12. It's taking the water level and going down to the 12, and now we're centered at the circle, okay? The water level's not really dropping. I'm just making a point that we're trying to shift this circle, and then I can easily make this width make more sense, okay? Now, why did they choose 12 minus y versus y minus 12? Doesn't this shift it down? True, but going way, way back into these other shell and disk method formulas that we've done before, what I often get if I flip those is a negative result. And so what happens is that you say, I got a negative force. So all you do is turn it around and make it into a positive. I totally agree, and that's good. But what would happen in this particular case in WebAssign is because you have two boxes, you're going to get them both wrong because, I mean, I guess you'll get this one right maybe because of positive, and then this guy is going to be a negative and not know what to do. You had to flip the answer or something. My point is it gets a little bit confusing, and I'm going to try to stick to, I guess, what you would call the book. And so we're going to use this style here for that shift. All right. 9.8 times the 1,000 times the integral from -7 to 7. This was forced onto us. This is my answer with the y's now. I got my 12 minus the y, okay? And then I also have the 2 times the square root of the 49 minus y squared. So again, that was my height or depth, and that was my width. So that makes the area. Now this is going to make my area of rectangles. It's just in the shape of a circle. Lots of little rectangles that end up making it look like a circle, right? So that's a circle, actually. There you go. Boom, done. Find the integral. There's your newtons. Walk away. You know that I do, if I do a little chuckle, yeah, no, there's a lot more to it still. But I gotta say that our answer is very close. So here's a strategy when you're doing the homework. This is not for exams or something, but when you're going through the homework and you see the problems with a box and another box, type this formula in and submit. See if it says that you're right or wrong. If you're right, then you know that you're on the right track. Just go ahead and find this integral, and when you're done with the integral, you'll get your answer and you know it's right. If you got this right but this wrong, you know that you integrated wrong and there was some kind of technical mathy problem, okay? If you got this wrong to start with, then you definitely have an issue with the concept and we have to start over there. Don't even bother integrating. So there's a lot of strength to at least trying that out beforehand. Again, on the homework, not necessarily on quizzes or exams, but it does help at least kind of get us by. I am not going to go through every single step. It would take forever, but I can at least show you the highlights. What happens is that I split up this. I basically take the 2 out, and I distribute the square root to both of these terms here. And so I've got 2 times the 9800 integral of 12 square root minus y square root dy. This is actually not too bad here. This is a plain old u substitution. It ends up very quick and easy, and you get an answer. This, not so much. This is actually a formula. I'm going to recommend formula number 37. And what it is, it turns into this crazy arc sign thing. Now, when I say formula, could we do trig substitution back from chapter whatever ago? Yeah. If you want to spend 30 minutes on it, that's fine. We've seen this before. Construct a triangle, got your theta. Here's your opposite side. Here's your hypotenuse is a 7. There's your y, blah, blah, blah. I mean, I guess it'll just take forever, but it's totally possible if you want to. Formula, very quick and easy. Here is my final answer. This is all together, okay? Here we go. And what I did here in this particular case is I took the 12 out as well. That's why I get a big number here. So, you ready? 2,35200 times 1/2 times y square root of 49 minus the y squared plus the 7 squared, arc sine of y over 7, close, 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 minus, so all this stuff here, minus the 19600 times, and I did the u substitution and stuff. I'm not going to go through every single piece there. The 2/3, 49 minus the y squared to the 3/2, close, close. All of this from -7 to 7. And in my notes, I actually just say there's a whole bunch of stuff in between, and my answer is 18103,113.51 newtons. And that's your answer. Wow. Okay. Next question. Next question. Got a lot more. So this next question is forcing us yet again to this particular integral. And I mean, again, I don't like that very much, but it's something we have to do. So I'm going to do it with you, of course. They say that G is equal to the 9.8. So you know we're talking newtons and metric system and stuff like that. My density is the 1,000 kilograms per meters cubed. Okay. And the picture is I have water, and then I have this triangle. It's an equilateral triangle with 10, 10, and 10. And it has a depth here of 5 square root 3. And they say find the pressure of this triangle in the water. Well, looking at the triangle, and they already gave you the 5 square root 3. Yeah, guess what this height is right here? It's 0. So we're going from 0 to 5 square root 3. That's pretty easy. Again, this is going to be my area. Okay, and then this is my final force here. This will be my force. Okay, so how do I find my area? Very much like the last time, I have an equilateral triangle, and what I need to do is take these little rectangles that construct it, And so each little rectangle is going to have a width times a depth. And because the depth here is always like from 0, it's centered at 0, I guess you can say. I could just use like an X or a Y or whatever. I'd like to use a Y, but here's a problem. If you notice, it's dx. And so you need to type here. You need to type x's, okay? I know that sounds weird, but this is actually an x value. And that's the sort of stuff that gets me. Like, we're forced into doing this, and now they're forcing us to use x when obviously it's a y value. And that just, it irks me, okay? So, okay, moving on. I want to find the widths of everything here. And so what's the width up here at the very top? Yes, you got it. It's 10. 10 width. What's the width at the very bottom? It's actually 0. And we have a linear progression here. I have at x equals 0, I have a width of 10. At x equals 5 square root of 3, we have a width of 0. And what we actually are creating here is an x and y kind of coordinate system, something here. And you can find the line. I mean, I'm not kidding you. It's basically this y equals mx plus b kind of thing in order to find all this stuff out. And so you find your slope and blah, 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 and all that stuff. Well, let me give you the answer. It's 10 minus 10 times x over 5 square root 3. Now let's talk about this for a second. This is my width. This is my width, total width, okay? Because again, I was measuring all the way across in this particular case. I start with 10, but then I'm removing some. Do you see that? I start with 10 and I remove some. How much am I removing? I have to remove all 10 eventually. Yes? But when do I actually remove that 10? When is this 10 going to be a 10 minus a 10? Well, when this guy is equal to a 1 right here. If this guy's equal to a 1, what's going on is that this right here must then equal the 5 square root 3. Therefore, 5 square root 3 and 5 square root 3, they cancel one another out, leaving a 1. 10 times 1 is 10. 10 minus 10 is 0, which gets us that 0 at the bottom. But what if I had plugged in instead a 0 here at the very top, you know? So then I would say, well, this whole thing cancels, and it leaves me with a width of 10. And so that formula works on this situation. That's just the width, not our actual depth. And so here we go. The 9800 integral from 0 to 5 square root 3 of, and here's my area. You ready? My depth is an x. My width is this 10 minus 10x over square root 5 square root 3 business, dx. Again, this whole thing is my area, but this is my depth, okay, or height, or whatever you want to call it, of a rectangle. And this right here is my width. So I'm deconstructing my area into height times width for each rectangle, basically. Okay, cool. And we're done here, right? Ta-da! Yeah, we're done, but we have to go and solve it now. Thankfully, this is not as hard. I'm going to distribute my x. And so we get 10x minus, and here we get a 10x squared over 5 square root 3 dx. And this is a pretty simple integral here. Add 1 to the power, divide by new power. Same thing on this side, blah, 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 blah. I'm not going to go into this one for time's sake. You get an answer of 1,225,000 newtons. And there you go. So apparently I just decided to start making a formula. So this is my force formula. Is this density stuff times the gravity, sometimes those are combined, times the integral of area dy. And why? Because, again, I'm looking for it in terms of height and stuff. And as we've seen again and again, my area is often deconstructed as a height. Oh, I just zoomed in. Sorry. There. I want to zoom out because that's not... Oops, wrong way. Sorry. Okay, there we go. My height times a width. And what takes the most time often is that width portion of the area. Another one, 83008. So apparently this is the exact same thing as what we've just been doing, but it does have a different style. It's the same thing. It's just going to be a different formula at one point. So let's go through this. I have a tank of water, but it's not filled all the way. And then at the very bottom, I have a half circle, a semicircle, and it has a radius of 5, so therefore diameter of 10. This was 30. Again, these are all in meters, and this is 6 meters. And so then it's the 9800 again, integral of your area dy. So we're good here, right? We're done. That's it. Get your answer. Yeah. Not really. No. We're going to do a lot more math, of course. So instead of doing this, I'm just going to refocus my picture and say, hey, why don't I just call this guy here 24? That'd be pretty easy. Notice again this height here, 5 and a 0 from the bottom. And so we can start from the bottom and go up or whatever. I drew a cool little picture here of what this looks like more zoomed in. And so what we actually have is a 5 radius, but a 10 diameter. Remember that we're looking for width a lot of times. And so when we're doing width, I'm going to want a 10, so 2 times whatever formula to make it work. I'm going to say that this is a y equals 5, and then that this right here is a y equals 0. And what we're going to do is I'm going to say this is cool because now I'm centering my circle, makes it super easy, right, 0 and 5. But I have to shift down everything by the 24 to get the correct pressures and stuff like that. So here's my, I guess you could say my final answer. My force is going to be that 9800 integral from 0 to 5, like I want, makes it easier this way. My depth is that 24 minus y, which we saw earlier. I've got 2 times the square root of 25 minus the y squared dy. Okay? 2 times because, again, I'm doing twice the amount, the plus and minus. We've seen this formula before with a circle. So, again, that's just 5 radius. We've already done that, and we've done this part as well. I said we already saw this. This is going to be U substitution, formula number 37, blah, blah, blah. And I have this huge thing written out, so I'm going to give you one of my, I guess, middle steps, I guess. And so this is just crazy huge. But at least it's a copy-paste of what we've already done on a previous problem. So I guess you can just kind of go back and reference how I was doing that. I'm guessing 2 negatives make a positive. I don't have a whole lot of notes on these because a lot of times I just skipped it. Mainly because, again, the point was my setup. And I'm hoping by now you actually have the ability to take the integral of these guys. And if not, guess what? There's formulas. That's what I've been using. Again, that should end up in newtons. You don't need to put the commas in for your answers. I do them because we're humans and we need that. Okay. Done with the first half of this section. Wow, man, there's another half to this. Yes, but this half is much easier. There's actually only one complex problem, and I feel like this next half is fun. So let's move on. And brand new problems, totally different than what we've been doing, okay? So imagine we have a number line starting at 0, going all the way to 30. And so we have a 10, and we have a 20, and we have a weight right here. And the weight has a mass of 8, okay? And then over here, we got another weight, and the mass, it has a mass of 12 at 30. And so they want 2 things. They want a capital M, and they want an X bar. That's, again, X bar, because it has a little bar on its hat. And they say, okay, go, figure it out. What? What is that? Well, what this is here is center of mass. If you've taken statistics, then this means like an average. And that's exactly what's going on. This is an average of what's going on here with my my weights. The capital M is called the moment. It's called the moment, and it's actually simply an intermediate step to be able to find your final answer. In a way, I actually could get the final answer first, and then I go back and find the moment a lot of times. But as we go through the rest of this, I'll show you how to do all this easily. Well, here's the ultimate question. I really want to get this across. This X bar, the center of mass, this average, I want to know where do I have a pivot on this seesaw horse. Is the sawhorse a seesaw? I don't know. You know, with the two kids, and you got the little thing, and they're going back and forth, up and down, up and down. You know, it rocks. So I can't remember what it's called. Seesaw? Sawhorse? I don't know. Whatever. Moving on. Where's that pivot in order for these to be balanced? Exactly. So you have a child that weighs 8 and a child that weighs 12, and there's some distance now. They have to scoot up or scoot back a little bit so that they're exactly level with one another, and they would balance each other perfectly. Okay, so where would that pivot be? Is it over here? Is it over here? Well, no. Humans are really good at just judging about this stuff. A little bit heavier, so a little bit closer to that side. As another example, what if I have something really light but something really heavy? So then to make it possible to be balanced, it would have to be very close to the side, if not almost right on it maybe. And that way it counterweights just enough so that it will actually balance itself out, okay? So I know about what my answer is. I mean, I don't know, 21 or something like that. That's my guess, okay? That's my guess. It's not 20. 20 itself is not going to work. It's like 21, 22, 23, something like that in order for this to work. So that's my guess. How do I go about finding the answer? What I'm going to do is, okay, I see. Yeah, I do actually just find the answer first. Here's your formula, I guess you could say. My x bar is going to be equal to m1x1 plus m2x2 divided by m1 plus m2. To be more clear, what I'm actually doing is this formula right here, and this is called a weighted mean or weighted average, okay? Weights because there's different weights at the different positions that we have. This is statistics. Of course, now, I'm not actually doing statistics here. I'm just going to be plugging in some numbers. So my first mass was an 8, and the x, where it was located, was at a 10. My next one was a 12 mass, and it's located at 30. And then I'm dividing it by the 8 and 12 together. I'm going to do some bad math to show you why this formula works. This is bad math. Don't even think about it. Wouldn't these summations cancel? Wouldn't these m's cancel? Didn't I get an x? Isn't that my answer? See? X equals x, right? Right? That is not good math. Do not do that. Do not do that. I'm doing that as a concept. The answer that we're looking for is x values. So I should here yield an x value, okay? That's what my goal is, an x value. So I have 80 plus whatever that number is. I don't know what that number is. I'm not going to do it. But my answer here from the calculator is 22. 22 is my my x bar. And wasn't I pretty close? 21, 22, something like that? See? I was very close. That's my final answer. Done. Here, like put it here, 22. You're done. There's nothing else to do there. Well, notice that we still have to find the moment. And it's not hard to find the moment. It's an intermediate step for something that we could already have done. What they're wanting is actually the numerator part. That is your moment. Your moment is going to be the m1x1 plus the m2x2. And so it actually yields a 440 numerator. And that's it. If they ask, and maybe sometimes they will, they want like total mass. And so then the 8 plus the 12 is going to be a 20. They didn't ask it in this particular question, but it is still something that you should be able to find. Okay, there we go. So that was an awesome little problem. Where was the calculus, right? Exactly. So we're going to do calculus in a minute? Maybe. Maybe. So M1 is equal to 4, M2 is equal to 3, and I got an M3 is equal to 3. And they give me a P1, which is at 2, negative 5. I have a P2, which is at negative 3, 3. And then I got a P3, which is at 3, comma 5. What is going on? They want MX, MY, and then X bar, Y bar, like this, with the parentheses already included on the outside, but you're going to have to include a comma on the inside. And so I'm just going to draw them roughly. Here I've got a 3 weight. Up here I've got another 3 weight. And way down here I've got a 4 weight. And I want to balance these. I want to put a pivot as if all 3 of these weights are sitting on a plate, like a dinner plate, and then I want to be able to pivot it somewhere. You've seen, I know this is a terrible example, but you've seen some people like balance something on their finger, and it's like, wow, how did you do that? Well, they just found out where the center of mass is. Now, if all these were 3s, I would probably just go right in the middle, but because this is a 4, it's a little bit heavier on this side. I'm going to guess around right here, maybe a little closer this way, kind of depending. But because those are still so far away and relatively similar, we would probably find it more in the center than what you think. Okay, so that's my guess, somewhere around here. I put my finger right here on the plate, and all of a sudden I'm balancing it, and everyone's like, ooh and ah. It's just center mass, that kind of stuff. So, how do we find this? I'm actually going to be doing the MX and MY stuff first, just because we have to actually find them and might as well do it properly this time. My MY is going to be the M1X1, the M2X2, and the M3X3. And my MX, sorry, red, black, whatever, M1Y1, M2Y2, M3Y3. Did I mess up? Oh, man, did I mess up? Did I mix my variables? Not again. No. Actually, this is correct. Yes, MY gives you an X value. It deals with the X values, and MX deals with the Y values. That is a big pet peeve of mine. Not something I can actually change because I'm just a little guy in life, but yeah, that is really upsetting to me that they do that. Now, what they're trying to say is it's the moment in terms of the axis that they give a letter of. So it would be the y-axis, and so my y-axis distances from there are x values. There's their explanation. Still upsetting. So my my, I have a, I'm going back through, I got 4 times a negative 5. Nope, this is my. Again, I'm doing the x values. Grr. I got 3 times my x values a negative 3. And I got a 3 times my x values a 3. Those guys cancel. I get an 8. My mx, I'm going to now do the y values. So negative 5, 3, and a 5. And all I'm doing here is pairing them up. See, there's my x values. And then my y values. I'm just pairing them up. That is all I'm doing there. See? That's all it is. And this came out to be a 4, by the way. I can use those now. So my x bar is going to be my divided by little m. Again, that's going to be the summation of my m's. Well, I already got this one. It's going to be an 8. But if I add up all the total m's, I got a 4, a 3, and a 3. So that's a 10. 8 over 10 makes 0.8. The next one, y bar, is going to be mx over m. Again, they're always mixing things up. In this case, I got a 4 over that same 10. So then my answer would be a 0.4. And so my final answer for x bar, y bar looks like this in WebAssign. It would be x is going to be my 0.8, y is going to be my 0.4. And like I thought, isn't it really, really close to the center? I mean, not perfectly, but pretty close, and that's what we got. Very close to the center. Cool. I have 2 problems left, and one of them's super easy. So, 8.3.014. I have y is equal to 4x, y is equal to 0, and x equals 1, and draw a picture, find the center of mass. So x bar, y bar. I don't think they want the moments in this one, thankfully, because that would have upset me even more, because my method does not require moments. Let me show you. I was smiling. You can't see that, though, I guess. What we have is a triangle, and I don't have the best triangle, but this is a line. 4x, y equals 0, right there, and x equals 1, okay? So I got a triangle, and they say, hey, find the center of mass for the triangle. And I'm going to tell you, it's about right here. Again, human eyes are pretty darn good at finding the center of mass. Where would you put your finger if you had a triangle here for it to all balance? It'd probably somewhere around right there. But let me tell you the mathematical side of it. I call this, and this is for triangles only, this is for right triangles. Are you ready? It's the heavy third. It's the heavy third, okay? That's the rule. So what I'm getting at is that this right here is a 1/3 distance, and this right here is a 1/3 distance. Notice that I'm trying to keep it, this is where the heaviest side would be, because again, it's not over here, because that's blank. It's not right here, because it's kind of thin. You're wanting to go 1/3 from, I guess, the heaviest corner, or opposite of the hypotenuse. And it's better visual than actual computational, but 1/3. Now, 1/3 is a distance, and so it's not an actual coordinate. And so what I'm getting at is that you can't just say, oh, 1/3 and call it a day. This right here, what's the height? Well, when you plug in a 1, you got 4 times 1 is actually a 4 height. It's not 1/3 then. I'm saying it's a third of the 4. I'm saying 4 times a third, and that equals, well, in this case, 4/3, or 1.333. And so right here, this guy is at a height of 1.333, okay? There's that zoom in stuff again. Sorry. Zoom out. All right, there we go. Close enough. So that was actually pretty easy. This, I believe, that's it. You're done. That's your y value. So that's your y bar. Pretty simple there. For the x's, it's a little different, because right here is where I'm wanting. Now, this is a 1, and so I'm saying this is actually going to be a third. What's a third of 1? 1 times the third is a third, right? But is this actually right here at x equals 1/3? The answer is no. Because right here is 1/2. 1/3 is actually over here. What is this guy? It's 2/3. It's 2/3. And the reasoning behind it is because we have, yes, 1 times 1/3 makes my 1/3, but it's the heavy third. So this actually started from the 1, and I went backwards. I started from this heavy side 1, and I went backwards a third to yield 2/3 as my actual answer. Okay? So it's like a number line still. Where's this ending up? 2/3. It's past half. At least you can say it's past half. And so is 1/3 more than a half? No. 2/3 is more than a half. And so again, that's going to be my x value, my x bar. Final answer here, very simple at this point. X bar, y bar. I have 2/3, and I got the 4/3, and we are done. Literally nothing else to do. Cool, huh? Is there a catch? Well, it only works with triangles. So, last problem is one that's not a triangle. E to the x. And I got y equals 0, x equals 0, x equals 4, and they want to find the center of mass, given these bounds and all that stuff. Well, e to the x looks something like this. Starts at 1. I got y equals 0 is down here at the bottom. X equals 0 is right here. And then x equals 4 is somewhere off in the distance there. And they want to know what's the center of mass for this weird shape. Human eyes tell me it's somewhere around, actually I'd say around right there somewhere. Maybe a little bit on this side. So not exactly 2, but it seems like it would be heavier. I don't know. It starts at 1, so maybe it would be a little bit higher than 1. But that's a lot of force right there. It's probably less than the 1, but more than the 2. That's my guess. It's somewhere around there, and we're going to see exactly what that is. What is my formula? So let's go back to a formula that we do know already. X bar is equal to my over m, and y bar is equal to mx over m. Okay, so those we know. Little m is actually pretty simple to find. It's going to be the integral from a to b of f of x dx. Now, technically, this is going to technically be top minus bottom back from the very first section in this class. But I don't want to go technical on you right now. Just, it's your integral. Easy enough, right? My, again, dealing with x values, it's going to be your integral from a to b of x times f of x dx. I hope that that also looks familiar to what we were doing back in the day. If I put a 2 pi in the front here, doesn't it look like shell method? But I'm removing the 2 pi, and I get this form. Just a thought there. And then I got mx is going to be 1/2 a to b of my f of x. Try that better. Squared dx. Doesn't this look familiar? What if I put a 2 pi in the front? Wouldn't the half and the pi, or half and the 2 cancel, leave a pi? Blah, 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 squared. Capital R minus little r. Did I do that? Washer method, this method? I don't know if I did that. I might have just said top, bottom. That's more my style. What I'm getting at is you've seen these formats before back in disk and shell method stuff. It's just that we're not rotating here. No 2 pi's or anything like that. We're simply finding the moments. Given that we have these formulas, it should be pretty easy to be able to find the final answers. So my little m is going to be the integral of 0 to 4 of e to the x dx. I mean, that's really all it comes down to. So we got e to the x from 0 to 4, e to the 4 minus 1. That's my little m. My my, again, dealing with the x values, I got 0 to 4 x e to the x dx. This is actually an integration by parts format. You got, this is your u, du is dx. You can say your dv is e to the x dx. V is equal to e to the x. Okay. And so your integral answer is uv minus integral of v du. And we already know that answer as well. It's just e to the x. Again, from 0 to 4. You plug it all in, and you get 3e to the 4th power minus plus 1. I'm sorry, plus 1. And that's my formula, or that's my answer for my. Mx, again, dealing with the y values, half 0 to 4, e to the x all squared dx. So what you actually have is e to the 2x dx. And so when you integrate, you have to do the u substitution, I guess. But in the end, honestly, you're just dividing by a 2. 0 to 4. And so my final answer here is 1/4 e to the 8 minus 1/4. Final answer, as in like final answer here, is again going to be my my over little m, my mx over little m. So here we go. We need, and this is just silly here, 3e to the 4 plus 1 all divided by e to the 4 minus 1 comma 1/4 e to the 8th minus 1/4 divided by e to the 4 minus 1. Type that in. Don't simplify. Why would you simplify that and sit there for 15 minutes doing that? Nobody wants to do that. Don't do that. Type it in. Get it done. I don't care what their answer is. Yours is right. Thank you very much. Have a great day.